right, so here is the question that has been asked of me by many students. So I want to give some major props to some of the students who really kind of not letting this one get away from me. This question was slide number 20, and if you look over here, 20 and 21, these were like the extension questions, or they called them challenges at the end of our area DESMOS activity. Now, absolutely, they were challenges. We then put out a message after that said, hey, just think about the process. What could you do? What do you think might work in order to find that little sliver of space at the top? This turned out to be a very challenging question, as did number 21. Slide number 21, I'm going to provide a link in Schoology, right where you see the same answer for what I'm going over right now. And slide number 21, I would not worry about that in any way, shape, or form. Slide number 20, though, this one right here, this is a cool one. And this one will require one skill from 8th grade to the Pythagorean theorem, which we actually did, believe it or not, on the first day of 7th grade, just as a little front loading. But this one does actually come together a little bit easier and a little bit more understandably than slide number 21. And here's how this one goes together. So what we know from the beginning is that there's two circles, A and D, and the center point A and the center point D, actually they kind of overlap. So D overlaps to the center point of A, and then the outside or the circumference of A overlaps to D. They also have a square created, okay? And that square created, it tells you, is AD is going to be a side to square A, B, C, D. So we know it's a square because it says it right there. We also know that it's going to be a 10 inch by 10 inch by 10 inch by 10 inch, so 10 by 10. So the things that we know right off the bat is that this is going to be worth 10, this is going to be worth 10, this is going to be worth 10, and then we can create our square, and everyone can say, well, 10 by 10 is 100. So we have 100 units, or we're going to call that inches squared. And what we need to do is remove everything that's not in that little black space, so we can find out what the little black space is right there. Now, my original thoughts was I tried to go and say, well, this big rounded ball diamond, if I find this big rounded ball diamond space, like right here, so if I find this, we know that that's going to be 1/4 of 314, and that turned to be 78.5. And I also know that this turns out to be 78.5. But the thinking there was I couldn't come up with a way to figure out how this overlap piece works, and that was a challenge. So looking at it from a different standpoint and reaching out to multiple other people to help figure this one out, what we can do is we can say, well, if the 10 goes from the center of A to the outside of A, well, then this would also be 10, because this going right up here is touching the edge of circle A. Just like this is the center of D, and we know the center of D to anywhere on the outside of D, we know that's going to be worth 10 as well. So then this must be also 10 if I take that into a triangle right there. Boom. And what you've created is a 10, 10, 10 equilateral triangle. So now we have a triangle in the middle. We know this is 10 across. We know this is 10 up here. We know this is 10 down here. So now, from this point, this is where we're starting to get a little bit funky. Okay, we need to find the area of this triangle. To find the area of this triangle, I do need to know the height of this triangle. And as we found on the first day of 7th grade, that's not an easy task. This actually involves finding, using the Pythagorean theorem. The Pythagorean theorem is a squared plus b squared equals c squared. I'm not going to go over that right now because that's not something that you need to worry about in 7th grade. I will tell you that we know this part to be 10. All right. We know that the formula for the area of a triangle is going to be area equals 1/2 times the base times the height. I'm just going to kind of put these pieces in here for us. Okay. Area equals, we know the base right here is 10. Okay, so that's going to be 10. I'm going to do my 10 times the 1/2. So my 1/2 of the base, that's going to be worth 5. All right. So that's going to be the base right there and the 1/2 going together. So 5 is going to be 1/2 of the 10. Now all I need to do is multiply by the height of this triangle, which is going to go in here. I'm going to spare us that time right now because that's using the Pythagorean theorem. But trust me when I tell you that the height of that triangle is the square root of 75. And that's a challenge right there. So the square root of 75 is in fact the height of this. So to find the area of the triangle, we need to do 5 times the square root of 75. So when calculating 5 times the square root of 75, it's an approximate because it's a big long number. It's approximately 43 43.3, and we're going to stop it there because it's 43.30127. So it goes on forever and ever. It's a non-repeating, non-terminating decimal. So with that said, we're going to say that that is the area of this triangle. We found all the space in there. So now what we need to do is figure out what's still left. I'm going to just kind of do this because we've got all this accounted for. What's not accounted for, I'm going to change colors, is these little, almost like a pizza slice, right? So this piece right here, which is going to drop down into here, which is going to drop down into here. Right? So we need to find that pizza slice. And then we have another pizza slice, which goes like this over here. And that pizza slice drops down into here. So we need to find those two pizza slices. Now, the question is, we can think about this. We can picture that pizza slice right there. And then how many of those pizza slices is it going to take to get around the outside? Like how many of those would go all the way around? Okay, like how many can I put? There's another one there, another one there, another one there. So the question is, how many of those can I put around the whole circle? Well, to do that, we're going to do another mathematical move. And we're going to say, first of all, if this is an equilateral triangle, we know that the inside of all triangles must equal 180 degrees. Okay? So this equilateral triangle in the middle, this red one, this is going to be 60 degrees here, 60 degrees here, 60 degrees here. And that's because it's 60, 60, and 60 equals the 180. Now, if that's 60, that means that this must be 30 degrees right here. So I'm going to make that a different color. This orange angle right here must be 30 degrees. Now, we know that a full circle is 360 degrees. And if the full circle is 360 degrees, I can divide that by 30 degrees. And that's going to tell me that we would have 12. There would be 12 of this pie slice per circle. 12 of this pie slice per circle. So I would take that right there would fit around here 12 times, just like this one right here would fit around here 12 times. Now, that's a challenge, and that's pretty cool to figure that out. But now that you know it's going to fit in there 12 times, what we can now do is say, oh, yeah, I remember that the area of this full circle was 314. So 314 inches squared. Okay, that looks like a 9, but it's 4. 314 inches squared. And if we take that value and we divide that by 12, okay, divide that by 12, that's going to tell us what one of these little slices would be, because we want just 1/12 of the full circle. So then 314 divided by 12 is approximately 26.16 repeating. Okay, so we'll probably just call that 16 or 17. But remember, we don't have just one of this value. We have another one right over there. So we're going to have to multiply that by 2. Now we're looking at 52. We'll say 1617, we'll say 34. Okay, so for 34 hundredths. So 52 and 34 hundredths. Now, that value is going to represent both of these orange guys, these little sectors. They're called sectors, by the way. Sectors of a circle. Okay? So the sectors of a circle, that one and this one combined give us that 52.34, or approximate value of 52.34. Okay? Now, this, remember, was the red circle in the middle. If I combine these two values together, that's going to give us everything in there except for that sliver, which we need to then take away from our square, which was 100. So if we add 43.3 and 52.34, that's going to give us a value of, I'm going to make some work up here, that's going to give us a value of 95 and 64 hundredths. So 95 and 64 hundredths. So the question is then, well, if I had 100 in the full square and I subtract away this 95.64, it's going to give us the grand finale answer, which we'll put in black since it's actually right there, the shape itself. Okay. This little sliver of space right here that we're looking for is going to be 100 minus the 95.64. So we're just going to call that approximately, I'm going to use my wavy equal sign, approximately 4.36. So 4.36 inches squared is the answer. And again, that's an approximate 4.36 inches squared for the little sliver of space that sits right there. Absolutely a challenging question. Absolutely a rock star effort by multiple kids in the class. I want to give them a major shout out for not letting this one get away from me, making me stick to it. And I really enjoyed doing that. I actually got to reach out to a former teacher, and she's now at central office. So major props to Lori Marple for helping us figure that one out. That was a cool question. Certainly a ton of work, certainly big brain thinkers out there. But I love the fact that we got kids in seventh grade math who are being challenged and who are not letting this one get away from them. So now they can pass this on to all the people that were trying to solve this question. And I thank you for your time. Have a great day. If you have any more questions about this one, let me know. Bye-bye.